Hello, I am doing my best here to follow along with Dr. Physics A's Einstein field equations for beginners, starting at around 44 minutes and 8 seconds and ending around 52 minutes and 28 seconds. In this article that I've posted on spoon-fed relativity, I find the method I would ordinarily use to find the length of a differential path element, dr d theta. Let's see, this is the dr, this is the d theta. Dr d theta in two-dimensional polar coordinates is given by a different formula than the one given at 4935. Let me see the one. Okay, this is the equation that it gives at 4935. And this is not the only place I see this equation written. I find it also in Lecture 7 of Warwick Physics. And what I found earlier was that I did not get the correct answer using this formula with a pretty basic example where I think it should have worked. And the main problem with it was that instead of having delta mn canceling out this del xm del xn term and this eta gamma delta canceling out this gamma and delta term, this really needs to be crossed out. This and this really need to just share indices. And so this would be gamma. So those really need to share indices rather than so that they cancel out naturally. Now you can see that I uploaded Einstein notation as matrices part 2 on December 24th. It's now January 5th. So it was 12 days ago when I worked through this originally, and I just want to go through it again and see if the mistake that I thought, or see if the error that I thought was there actually is still there. Which means I'm going to try to compute this ds value in 3 different ways, the same 3 different ways that I did on December 24th, or before December 24th. The first way is the simplest, not real simple, but still much simpler than the other ways. Let's start by saying that x equals r cosine theta. I don't like that color. X equals r cosine theta and y equals r sine theta. So x and y are Cartesian coordinates going this way and this way. And so this value of ds over here is going to be ds squared equals dx squared plus dy squared. That's just the Cartesian coordinates, or what am I saying? It's the Pythagorean theorem. So ds, we don't know what ds squared is yet, but dx squared would be the del x del r dr plus del x del y dy squared plus dy squared would be del x, wait a second, sorry, del x del r dr plus del x del theta d theta, and then dy squared would be del x del y del r dr plus del y del r del theta d theta quantity squared. Now I wanted to write that as a matrix multiplication, and this is essentially what I have. But let me kind of go through some steps of getting there. This isn't copied from another source. This is just what I would do if somebody told me to express this as a matrix multiplication. And to think about that, this del dx is the matrix multiplication of, or it's the inner product of del x del r del y del, I'm sorry, del x del theta times dx dy. Sorry, is that right? D theta, dr d theta. Yeah, okay. Okay, if I didn't make any mistakes, then I'd be perfect. But that's why I catch so many mistakes. Why I might catch a mistake that other people wouldn't, because I make so many of them myself. Dy equals del y del r del y del theta times dr d theta. And if we wanted to make that dx dy as a vector, then we could write it dx dy equals this whole thing, del x del r del x del theta del y del r and del y del theta times dr d theta. Now it is noted that dx dy, this ds squared, is essentially, I mean, it's dx squared plus dy squared, right? But some people have noticed that it is actually the inner product of dx dy with dx dy. Now, if I have an inner product composed of a vertical vector like this and a horizontal vector like this, I need to not only transpose it, but reverse it. So I'm going to write this one in reverse, so that it goes dr d theta, and it's going to be the transpose of this matrix here, del x del r del x del theta, and then we'll have del y del r and del y del theta over here, and then the rest of it is just copied down. And because I have cool software, I can actually just pull it down like that. And that should be what I have up here. Del x del r, del x del theta, del y del r, del x. Yep, okay. So now, how would I write that in Einstein notation? Well, first of all, I'm going to come up here and look at what they have, MR, MS. So I'm going to try to do that with this thing. Now, this is M, this is R, this is, they said N here, and they said this is S, right? Let me check again. No, I did it all wrong. Okay, the idea is that this del x and del y, this top part goes horizontally. So I'm going to put a little arrow right here to say m goes to the right. So this is m going to the right. This has also x, it says x and y going down. So this is going to be n going down. This has del y, r, the bottom part, so that's going to be the del r del theta on the bottom going down. So that's r going down, and this is down. And then the del y s, del r del theta, the s direction in the matrix is s going to the right. So s goes this way. So what ends up happening is I can, since this dr d theta is going to be canceling with these terms here, del x del r times dr plus del x del theta times d theta, I'm going to have another r variable going to the right here, and I'm going to have an another s variable going to the right, going down here, so it'll cancel out del x del r times dr plus del x del theta times d theta. That's the way matrix multiplication typically works. The only problem with this matrix multiplication is that if if these two terms don't match, if that index and that index doesn't match, then that shouldn't simplify the matrix multiplication. That should increase it. That should make it bigger instead of making it smaller or the same size. So in order to fix this, you would need to change this to an m coming down, and that would basically fix it so that it would represent this fairly straightforward matrix multiplication, and it would have the nice advantage of giving at the end you would produce a scalar, which we expect out of ds squared. Now it would take a little bit of time to actually do all of this, but del x del r, since x is r cosine theta, del x del r is cosine theta. Since del x del theta, or since x is r cosine theta, del x del theta is like minus r sine theta or something like that. Anyway, if you actually do add this together with this, there's a whole bunch, the trig properties cancel out. Cosine squared theta plus sine squared theta equals 1, and everything cancels except for that ds squared ends up being dr squared plus r squared d theta squared. And nothing really changes if you multiply it out in matrix form. You might do things in a slightly different order, but you should come out with the same answer. But I wanted to see what would happen if I used, what would be the case if you actually use the Einstein metric, what we have from those two sources that I pointed out earlier. And I called this the alleged metric because, and I changed the order of things, the arrows a little bit to give out so that the little double down arrow and the double right arrow indicate kind of a submatrix inside the big matrix. Whoops. This little notation here, the boxed sigma, capital sigma, is kind of a new notation. It doesn't exist in matrix multiplications, but it's called a sum of products. It's kind of like a dot product, except instead of doing a dot product, I'll kind of come down here where it becomes evident. I'm going to take 1 times this matrix plus 0 times this matrix plus 0 times this matrix plus 1 times this matrix on this side, because I'm going m down corresponding to the m downs over here, the n rights corresponding to the n rights over here. And then when I come over to do the other side, all right, we'll come over here, and then once we do that, we'll have a 2 by 2 matrix, which is this plus this basically, and this matrix plus this matrix is essentially what we're getting out of it, because it's a 1 year and then 1 year, 0 there and 0 there. And then we'll take this matrix, this plus this, cosine squared theta plus sine squared theta times dr squared, plus minus r cosine theta sine theta plus r sine theta cosine theta. That would be 0 times dr d theta. And then we would have r cosine squared, or no, negative r sine theta cosine theta plus r cosine theta sine theta. That would also be 0 times d theta dr. And then we'll have plus r squared sine squared theta plus r squared cosine squared theta times d theta squared. And that would give us 1, or would just give us r squared d theta squared. So it looks like I made a mistake, because in this step I've got a plus 2 cosine theta on this step. 1 times this matrix here plus this matrix here is not going to give me plus 2 sine theta cosine theta, is it? it's going to give me minus r cosine theta sine theta here, plus r sine theta cosine theta there. Well, that's actually good news. That means that this method actually does produce the right result. And so I am not stuck at shaking my fist at general relativity theory this early. I can move along saying, as usual, when I think I found a mistake, it's mine. And I don't think there's any good rhyme or reason to this mistake. It's just that I did it wrong. Probably because when you're inventing a new notation, when you're inventing a completely new way of doing things, you might make some errors in applying it. I've had a few days to kind of forget and remember what I was doing here. But definitely one, if I multiply this with m going down and m going down here, this 1 is multiplied by this whole matrix, and this 1 is multiplied by this whole matrix, and then they're added together. That's what that sum of product thing means. So this is definitely an error. This is 2 cosine theta 2 sine theta cosine theta should not be there, and this 2r squared cosine theta sine theta should not be there. Now I still do think that that method of creating this thing with the 2 by 2 by 2 by 2 matrix is a little bit awkward, I guess is the word. Philosophically speaking, I could ask, is the Pythagorean theorem really a case of a dot product of a vector with itself? If you do think that, mathematically speaking, the Pythagorean theorem is an instance of a dot product of a vector with itself, then even if you did think that, then I would still think that this would be the way to expand that dot product as a matrix. I don't know if just because the math does happen to work in that instance, well, we see here that it's not altogether necessary to invoke a third and fourth dimensionality of these tensors. We can do it with 2 by 2 matrices all the way through. Now I can see that this 2 by 2 by 2 by 2 tensor does appear just by changing that m to an n, and we have the added advantage maybe that this alleged metric is actually commutative, and it probably has an additional added advantage that we can stick in an eta m sub n term here, which is going to make it possible to put in something that has like a Lorentzian metric, or do you call it a Minkowski metric? Something like this with negative ones along the diagonal. Anyway, those are questions I will be posing in later pages on my Spoonfed Relativity site. Thanks for watching.